Hello everyone. Let's continue our discussion on defining the width and height of core and die. So we looked into how do we come up with a utilization factor and the aspect ratio terms and some examples for it. So let's take another example. For example, we have this square shaped chip. Okay, and the dimensions of this particular chip are something like this. You have the core height as 4 unit. You have the core width as 4 unit. And now let us try to calculate the utilization factor and aspect ratio. Okay, so what we'll do, we'll place our existing circuit onto this particular core, and this is how it looks like. Let's say we place it somewhere over here. Okay, now in order to calculate the utilization factor, you need the area occupied by the netlist, which is nothing but 2 into 2 units, which is 4 square units. Okay, this is the area occupied by the netlist, and the total area of the core. You have the height as 4 unit, you have the width as 4 unit, so total area of the core is 4 cross 4, which is again 16 square unit. So 4 square unit by 16 square unit, you have it as 0.25. So it says that out of the complete chip area, 25% of your chip has been utilized. Okay, and the remaining 75% is available for you for optimization and for all other things. So 25% of the core area has been utilized by the initial netlist, which is completely connected by wires, or which will be completely connected by ideal wires, which don't have any shape or size. And you have 75% of the chip area available for you, where you can place the additional cells, where you can which can be used for routing. Also for routing, there will be some more layers of routing. So basically, when we do a routing, this is on one layer. On the top of this, there will be one more layer, and where you will be doing the routing and all those things. So we'll talk about that in some other videos. So you have the 75% area available for cells only, for placement of the cells only. Okay, and now let us calculate the aspect ratio. So when we try to calculate the aspect ratio, it's height by width. It's height by width. So height is 4 unit, width is 4 unit, and you have your aspect ratio as 1. As talked about the aspect ratio in the previous videos, wherever you see an aspect ratio of 1, it is supposed to be a square chip. Okay, so this is how you come up with the width and height of core and die. The next point in the next step in this particular physical design flow, or in the flow of floor planning, is to define the locations of pre-placed cells. So before we go into defining the locations of pre-placed cells, let us try to give you a brief overview of what does pre-placed cells actually mean. Okay, so again we'll take another example. Let's take a combinational logic. So the assumption is this combinational logic does some amount of function. Okay, it does some function. Maybe it's a memory, or maybe it's a multiplier, or it's a mux. It's a complex mux, or it could be any clock divider, any complex clock divider, or so on. Basically, this combinational logic does some amount of job. Okay, and it does such a big task that the output of this combinational logic is a huge circuit. It's a circuit of, let's say, some 50k gates or some 100k gates. So it's a huge circuit. Okay, so there is a way that we did not implement this circuitry every time as a part of the main circuitry, but we can take this piece of the circuit out of the main circuit and then implement this separately. and even we can granularize this particular circuit itself. So if this was, let's say, 100k gates, we can divide this divide this circuit in such a fashion that you can make it actually 50k gates and 50k gates. You can make two blocks of 50k gates. So it looks something like this. So for example, let's take this particular circuitry out, and this circuitry is a part of your main netlist. Okay, let's take this piece out of the main netlist and do few things on it, do few processing on it. So what we'll do, let's try to cut this circuit into two parts. Okay, so we'll cut this circuit into two parts. This is one of the parts. This is one of the sections of the circuit. This is one of the sections of the circuit. Now the idea is we'll separate both of them. When they are attached together or when they are connected together, they perform some function. But right now we'll separate them out. Okay, something like this. So we have this cut 1, we have this cut 2. And we have this connectivity information. If you see, these are the connectivity information that you see. So A1 is connected to A5 in this fashion. We have all this information from the cut 1. We have all the information from cut 2. Let's try to separate this out as two different blocks. So now if you look into A1, A1 is connected to A5. So A1, the output of A1 goes to A5. The output of A4 goes to A6. The output of A4 goes to A6. Okay, these are two different blocks. Let's try to put it in that way. These are two different blocks, and this block will be implemented separately, and this block will be implemented separately. Let's see how. So we take these two separate blocks, two blocks independently, and give and extend the IO pins over here. So when we say, so our input output pins, basically these are the input pins of this particular block. This is the only output pin of this particular block. So let's try to first extend those pins, and it will look something like this. Okay, so this box will have this is the input side of this box, this is the output side of this box. Okay, now let's try to detach these two blocks. Okay, we'll black box this box and try to detach them. So when we black box this particular box, this section of the circuitry, or this section of the circuitry, is invisible for the one who is looking into top, who's looking into the main netlist. Okay, so now this section is invisible to the top netlist, to the netlist that we have implemented. This section of the netlist is invisible to the top netlist, and we'll separate them out. We'll separate this two boxes out, something like this. So this four outputs of this particular block will behave as four output ports. This four ports for this particular block will behave as an input ports. Okay, and this block will be implemented separately, this block will be implemented separately. The advantage of doing this is, for example, this block or this piece of the circuit is being replicated multiple times on your chip, or in this particular thing is being used multiple times on a netlist to perform certain function. You need not implement this one multiple times. You can just black box them. You can give this particular block to some user. You can give this particular block to some user, and those two users will implement these blocks separately, and that will be implemented only once. And then these blocks can be connected in this fashion multiple times onto the netlist, and can be used whenever it is required. So you did not implement this multiple times, you just implement it once, and then it can be reused. So this is the concept of reused models, where we have these small modules, and that can be reused separately on the top level, on the top net list. Okay, now for example, there are other IPs also available, readily available in the market. It's something like this. If you can have something like memory, you can have something like a clock gating cell, a complex clock gating cell, you can have something like comparator, you can have something like mux. So all of them can be implemented once and can be instantiated multiple times onto a netlist. So this need not be implemented multiple times, because this is a part of your top level netlist. They perform some functions, they receive some input pins, they receive some input signals, they deliver some output signals, but the functionality of this particular cell will be implemented only once. And that's what we call it as pre-placed cells, because these cells are being just placed once in the chip. That we have to define the locations or the arrangement of this particular cells, and this has to be done before the routing, before the actual placement and routing. So the placement of these cells on a top level chip will be fixed. And since they are placed before the actual placement and routing, they are referred to as pre-placed cells. Okay, so these cells are placed in such a fashion that the automated tool, whatever the placement and routing tool we have, that will not touch the locations of this particular cell. Once they are placed on once their locations are fixed onto a top level on a floor plan, they are fixed, they are not touched, or they are not moved by any of the automated placement and routing tools. Okay, so what we'll do is, since we understand what the pre-placed cells are, we'll try to take few of the pre-placed cells, or few of the cells, let's say block A, block B, whatever we discussed in the top. We'll try to take that cells and place it on a chip in such a fashion that their locations are not moved. And once they are placed, they are fixed in that locations, and the further steps will not touch those locations. Okay, so let's try to do that small part in the next video. Thank you.